Right, we're going to look at the problem given by one of your friends, right? Um, no question number here. So if you look at the book, the fifth edition is in problem 3129. Um, the solution given by the authors or someone else that I don't know that puts out a lot of effort to solve this problem. It just required you about one, two, three, four, um, 5 steps, right? And you get the answers that the velocity is 3.59 meter per second. I'm not going to use this method. Instead, I'm using the vector analysis method and then try to look at the um, solution of this problem. Right. So let's read some of the problem here. So we have a ball. It's released from position A with the initial velocity of 3 meter per second, and it will swing back and forth, right, in the vertical plane. At the bottom position, the cord, right, it strike uh, a fixed bar. This one is a plan view, and the ball continues to swing in the dash arc, right. This is the arc. We need the only problem here is to calculate the velocity of the ball at point C. I think C is here where the vertical distance is defined. Right, so let us look at the uh, uh, how this problem is being solved. First, I'm going to treat the motion of A to this direction and get the position vectors. Next, we look at the uh, uh, position um, uh, here and then to C, right? Get the position vector for B and C, and finally we look at the position vector from A to C. So this is the initial state, this is the final state. So let's go to the first kinetic state. So for we have the string which is 1.2 meters. The first angle we release is 60 degree, right? So we need to do a conversion from rectangular coordinate systems to anti coordinate system, right? So I think this one is based on cylindrical polar coordinate system. We have R and then we have theta coordinate system. So the angle made with the R coordinate axis with the uh, x axis is 330 degree. So we obtain the position of the ball at initial state A with respect to uh, O written in the cylindrical polar coordinate system 1.2 meters plus 330 degree in theta in polar directions is equal to 1.04 meters in x direction and minus 0.6 in y direction. Next, we look at the kinematic state at final position. First, we look at the coordinate position vector for point B, location B. And from there, I'm using also the R and theta coordinate system and also obtain the position vector in x and y directions. So the angle made with the x-axis and the r-axis is 270 degree, and the r position is 0.8 meters. So we express the position B with respect to O. Relative to O is 0.8 meters plus 270 degree in theta direction, and 0 in x direction minus 0.8 in y direction. For C to B, position C to B, right, relative to B, the position vectors, the R uh, position axis is about 180 from the x-axis, and the distance is 0.4 meters. So we have 1.2, right, 1.2 meter here, and then we have 0.8, so we have 0.4 meters, right. This one is 0.4 meters, and then we can get the position vector of C relative to B, which is in spherical polar coordinate system, 0.4 meters in R and 180 in theta degree. And then the xy condition is 0.4 minus 0.4 meters and 0j y direction. So from here we can get the absolute position of C with respect to O, right? So which is minus 0.4 and minus 0.8 j. So we want to know what is the position vectors from the initial state to the final state. So we use a vector analysis. We can find that the position vector of RCA is minus 1.44 meters in x direction and minus 0.2 meters in y direction. Minus 1.44 meters in x direction, minus 0.2 meters in y direction. Why we don't use r theta here? It's also possible to do it, but I don't think it's necessary. And then in order for us to evaluate the velocity here, I'm not using the work energy method. That would be your exercise, right? This is a free body diagram. This is the path of the body, right? And whether from A to B position and B to C position, the tension inside the string is always normal to the path. So this force does not do any work, right? So in order for us to evaluate the work net, the net work done by the ball to the surrounding, and the force work done by the force to the ball, this one is equal to 0. Then we just look at the changes of kinetic energy with the changes in potential energy. So this is a definition for kinetic energy, definition for potential energy, and after rearrangement, the mass of the ball can be cancelled using gravitational acceleration of 9.8, and we have the distance travels from A to C is minus 0.2 in y directions, and then the initial velocity of the ball is 3 meters per square. We get about 3.59 meters per second.